So in our last target, we talked about charges, and we talked about whether charges will attract or repel. We talked about Coulomb's law and the force between two charged particles. Now we're going to go ahead and we are going to talk about electric field. So electric field is kind of an abstract concept, but we'll talk about electric fields. We'll talk about how we represent them and how we calculate the strength of an electric field at some point around a charge. So our target is to be able to describe electric fields. So let's go ahead and let's talk about electric fields. The space around a charge where electric forces can act is what we call an electric field, right? Electric fields transfer electric forces. And usually when we represent electric fields, we'll represent them as a kind of series of arrows around a charge, right? So if you look at the picture I have up here, you can see a positive charge and a negative charge. And the arrows represent the electric field, right? You can see with just a single charge, the arrows just go straight out from the charge in each direction. Also notice that for a positive charge, electric field lines travel away from the charge. And for a negative charge, they point towards the charge. When we have a strong electric field, we represent that with many lines, many arrows coming from the charge or going to the charge. And when we have a weaker electric field, we'll represent that with fewer arrows, fewer lines going towards or away from the charge, right? We can also kind of describe what it looks like when the electric fields from two different charges interact with each other. You can see in this picture here, there's a positive charge and a negative charge. And so the electric field lines will move away from the positive charge out in every direction, and they'll move towards the negative charge from every direction. You can see they make a little pattern there as they go between the two charges. So, you can look between the charges and the arrows go straight from the positive to the negative. And as you get, further away, they make these bigger and bigger loops, right? We could also look at what it would look like between two similarly charged particles, between two positives or between two negatives. And I'll leave you to think about what that's going to look like. We can calculate the strength of an electric field at some point in space around a charge using the equation here. It says E equals kcq over r squared. E represents the electric field strength, right? E for electric field. And electric field strength is measured in newtons per coulomb, N/C, newtons per coulomb for electric field strength. Kc, of course, if you remember from our last lesson, is Coulomb's constant. That's 8.99 times 10 to the 9th, right? Q is the charge in coulombs, and R is the distance away from that charge that you want to find the electric field strength, right? And keep in mind, R there is squared. So E equals kcq over r squared. Let's go ahead and take a look at using this equation to solve some problems. Here is a problem for us to take a look at. It says, this is a simple one. It says, find the electric field strength 2.3 meters to the right of a positive 1.6 coulomb charge. So what I'm going to do first is let me write down what I know. So it tells me that the electric field strength is what we want to find. So E is what we're looking for. It says that the distance that we're looking away from that charge is 2.3 meters. R is 2.3 meters. And then it tells me the strength of the charge is positive 1.6 coulombs. So Q is positive 1.6 coulombs. Okay, the equation we just learned, it said E equals Kc Q over r squared. And of course, I also know Kc. It's 8.99 times 10 to the 9th. Okay. So let me go ahead and put those numbers into this equation here. So E equals 8.99 times 10 to the 9th times Q, which is 1.6, divided by r squared, which is 2.3 squared. Watch out for that squared. It'll get you every time. Don't forget it. Okay, so fairly easy equation. It's already solved, so let's just take our calculator and work out what we get there. So I have 8.99 times 10 to the 9 times 1.6 divided by 2.3 squared. And we're going to need, it looks like, two significant figures. Both of these numbers had two significant figures. So, wow, I get a large number here. I'm going to make that 2.7 times 10 to the, let me see, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. 10 to the 9th power. Okay. And the unit for the electric field strength, like we just talked about, newtons per coulomb. So there is a pretty simple example of using this equation to solve some problems. Things can get a little bit more complex when we have more than one charge and we want to find the electric field. Okay. Here's the thing: when you have more than one charge and you want to find the electric field strength between them, what you need to do is you need to find the vector sum of the electric field strengths from each charge at that point. Okay. Now, in order to avoid doing vector algebra here, like we did it back in the unit on two-dimensional motion, what we're going to do is we're going to kind of limit our problems to points that are either directly between or directly in line with the two charges. Okay. We could, using vector algebra, find the electric field at any point in space, but we're just going to kind of limit it ourselves so that we don't have to worry about so much vector algebra. Now, if we're asked about a point that's between the charges, we're going to subtract the electric fields from the two charges. And if we're asked about a point that's in line with them but not between them, then we're going to add the fields together. Okay, let's take a look at doing this. Here's the problem. It says a positive 2.0 coulomb charge is placed 23 meters to the right of a negative 3.0 coulomb charge. Find the strength of the electric field 9.0 meters to the right of the positive charge. Okay, now drawing a diagram here might be very helpful. So let's take a look at what we know. It says there's a positive 2.0 coulomb charge 23 meters to the right of a negative 3.0 coulomb charge. And then we're looking at it at 9 meters further away from that. So it sounds like my negative charge is the furthest to the left, and that will be negative 3.0 coulombs. And then some distance away, how much distance is that? 23 meters. I have this other charge, and that is positive 2.0 coulombs. And then we are interested in the electric field some distance further away, and that distance is 9 meters, 9.0 meters. Clearly not to scale, but that's okay, it doesn't need to be. Okay, so what we're going to have to do is we're going to have to do two different problems, finding the electric field here due to each of these points. Okay, so we'll use our equation, E equals KC Q over R squared. Let's do it for this charge first. Okay, so over here, Q is negative 3.0 coulombs, and R is, let's see, how far is this point we're interested in from here? So there's 23 meters plus 9 meters gives me 32 meters. Okay, so let's put those numbers in here. So the electric field strength is going to be Kc, which is 8.99 times 10 to the 9, times the charge, which was negative 3.0, divided by R squared, so divided by 32 squared. Let me grab my calculator and figure that out. Okay. And here I get the electric field strength from that charge as negative I need two significant figures, so 2.6 times 10 to the 1, 2, 3, 4, 5, 6, 7th power. And that'll be in newtons per coulomb. Okay, let me go ahead and find the electric field strength from the other charge here. Okay, so in that case, Q is positive 2.0, and R is just this distance here, which is 9.0 meters. Let's put the numbers into that equation. So E is 8.99 times 10 to the 9th times 2.0 divided by 9.0 squared. Okay, so let me work that out here. And there I get 2.2. I still need two significant figures. 2.2 times 10 to the 1, 2, 3, 4, 5, 6, 7, 8th power. And that'll be newtons per coulomb because it's an electric field. Okay. Notice this one's negative and that one's positive because they're in different directions. Okay. Now, we're dealing with a point here that is not between the two fields. So we said if the point is not between the two charges, then we're going to add the two fields together. So let's add these two electric fields together to get the total electric field here. So I'm going to grab my calculator. I'm going to take 2.2 times 10 to the 8th plus negative 2.6 times 10 to the 7th. And here I get 1.9 times 10. That should be 10 to the 8th. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. Yeah, 10 to the 8th. And that'll be in newtons per coulomb. Yeah, so a little bit more complex than the last problem that we did, but still not that difficult, right? If your point is not between your charges, add your fields together. If it is between your charges, subtract your fields. So there is a little bit about how we represent electric fields using electric field lines and how we can calculate the strength of an electric field at some point in space around a charge. So hopefully that helps us to be able to represent electric fields or describe electric fields. So until next time, take it easy.